Let us begin. This is one of the problem where you have been given incremental production cost of two machines and B coefficients of a system and set to operate or evaluate the scheduling like that. Okay, let us go ahead. Incremental fuel cost of two plants are given by DC1 by DPG1 by a value 0.075 PG1 plus 18 rupees per megawatt hour and DC2 by DPG2 as 0.08 PG2 plus 16 rupees per megawatt hour. This is the incremental fuel cost. Then the loss coefficients of this system are given by B11, B12, B22 in terms of fraction per megawatt. You can see over here. B11 is given, B12 is given, B22 is given. You might be knowing when two machines are interconnected to a system where system is suffering a loss, the loss PL is written as B11 PG1 square, B22 PG2 square plus 2 times B12 PG1 into PG2 was the equation we got it. Using that equation, we need to work out here. So that is the reason how many B coefficients are given here matter me. If two machines are there, in fact, I should get 4 values out of which B12 is same as B21. In case of 3 machines, if they were given, I am in need of 9 B coefficients, B11 through B33 like that. Okay. So in this context, 2 machines were given. I will be in need of 4 constants B11, B12, B21, B22 like that. They were given here. And lambda is 25 rupees per megawatt hour. Find the real power generations, total demand and the transmission line loss. So this is very interesting problem. It's a very lengthy problem, very interesting problem. When you see a B coefficient, surely you must come across what kind of problem is this? It is a problem based on penalty factor. Whenever you want to schedule several generator for economic operation, when the transmission line losses are mentioned, if and only if incremental production cost and penalty factor of that plant must be same for every participating generator. It means to say DC1 by DPG1 into L1 should be equal to DC2 by DPG2 into L2 should be equal to DC3 by DPG3 into L3, so on till the last generator. Then you are come across L1, L2, L3. Then what are these L1, L2, L3? Penalty factor. How costlier is that plant in producing megawatt additional is the indicator of that machine. Therefore, to calculate that, we require an equation. We know that equation for penalty factor is Li equal to 1 over 1 minus dou PL by dou PGI. Definitely PL is required for me. Dou PL is required later. In that context, we need to write first what is PL in this system. Look at the system. So PG1 plus PG2 should be equal to PD plus PL. Then PL is written as summation of block. This is expanded over here directly. It is B11 PG1 square, B22 PG2 square, 2 times B12 PG1 PG2. This is a split form. I am telling you in the abbreviated form. So you can see B11 PG1. You can see 0.0015 PG1 square. Is it B11 is 0.0015? Absolutely correct. B11 PG1 square plus B22 is 0.0032. You can see what is B22? 0.0032 PG2 square plus 2 times the value of this one. You can see 2 times the value of this one. 0.004, it became 0.008 PG1 PG2. Naturally, there is a minus I come out. This is actually PL. This is a loss which is going to incur in the system where these two generators are interfaced to deliver certain commitment. Now, what is that loss exactly going to happen is based on what set point PG1, PG2 get into. For that, again we know economic scheduling of several generators in a lossy system is possible where penalty factor is considered is given by dC1 by dP1 into L1 should be like that. dCi by dPgi into Li must be same. Then I will move to next right side page. What is that? Incremental transmission line loss. That is partial differentiation of equation PL with respect to PG1, PG2. So that will lead me further L1, L2, which will be used for my computation. For that, what I'll be doing? I will take differentiation of this equation PL with respect to P1 once. Let's see. It's being taken. You can see here. When I differentiate this equation with the Pg1, 2 comes out. 2 into 0.0015 Pg1. Okay. Minus 0.00 mean 0.0008 Pg2. Correct? And this is not differentiable because there is no Pg1 term here. You can see here. It's been done. Yes or no? Absolutely done. This is actually dou PL by dou Pg1, which is useful to find out penalty factor of plant 1. What is penalty factor of the plant 1? 1 divided by 1 minus ITL, incremental transmission line loss, whatever you have evaluated or computed. You have to write it. 1 by 1 minus bracket this whole term. You wrote it. This is penalty factor number 1 for plant 1. Similarly, penalty factor for plant 2, what I will be doing? This equation I will differentiate with respect to Pg2. Definitely first term I make it 0 because I cannot differentiate. Second term when I differentiate, minus 0.0008 Pg1 remain, plus 2 times 0.0032 Pg2 comes out. You can see here. Absolutely it's matched. Correct? 2 is multiplied already inside. 32 became 64 over here. Clear? This is used to get penalty factor L2 of the plant. When you got it, penalty factor of plant 1, penalty factor of plant 2, you just check the condition. Condition for the optimum operation is dC1 by dP1 into L1 must be equal to dC2 by dP2 into L2 must be equal to lambda. System lambda, commonly accepted cost of production. Therefore, I will just make product of dC1, dP1, L1 equated with the dC2, Pg2, L2 equated with what value? 25 rupees per megawatt hour given. They must abide a common lambda of 25 rupees per megawatt hour. Then I write the equation. You can see here. Incremental production cost of plant 1, the first equation, into penalty factor of first plant. Is it right? Should be equal to 25, as well as second equation, incremental production cost of machine 2 and its penalty factor should be equal to 25. That's what is the EIC, equal incremental cost criteria. When I do it, you can just see. When I multiply equal to 25, I will be getting an equation in terms of what? Because this equation contains Pg1 as well as Pg2. Carefully you have to watch. It contains Pg1 term, Pg2 terms. It will generate me an algebraic equation in terms of Pg1, Pg2 and a constant. Similarly, when I equate second term, I must be getting similar kind of algebraic equation. You can see here. Is it clear? Finally, I got a second equation. Now I got two equations. Equation 1 from penalty factor and incremental cost of first machine. Second equation from penalty factor plant 2 and incremental fuel cost of machine 2. Then on solving those, we get Pg1 equal to 52.247 and Pg2 as 41.852 megawatt. Means to say, till this time, I do not know what is the schedule of particular generator 1, 2 and what is the loss also I do not know. Now let's say when I have this production cost obtained and the values are substituted in the respective equation for lambda equal to 25 rupees per megawatt hour, it gained PG1 as 52.247 megawatt and PG2 as 41.852 megawatt. Let's write back. Then what is that actual loss then? Loss is using the equation. What was the equation? B11 PG1 square, B22 PG2 square plus 2 times B12 PG1 PG2 respectively, whichever the equation we referred at the footer of this page. Yes, in this PG1 PG2 respectively, I will substitute and get the value of PL. So this substitution of PG1 PG2 mean PG1 PG2 and PG2 square lead 7.95 megawatt as a loss. Then what is that exact load then? Demand. Demand is actual PG1 plus PG2 minus the loss. Is an ideal situation. When economic scheduling was worked out by the generators with the penalty factor concept, the total generation was exactly equal to demand plus loss. Now we got generations. Now we got loss. If I difference them, what is that I'm going to get is a total load. That's what is being done. So when I do it, 86.149 megawatt is the load. It was the load. To meet that load, there occurred a loss of 7.95 megawatt, which led the generator to generate 52.247 megawatt from generator 1, 41.852 megawatt from generator 2. It's very simple but little lengthy look, but you can do it very easily. You can do if you understand the requirement of this problem. You can do it. You have been given EICs, you have been given cost of production lambda, set to calculate generation, load and loss. 3 parameters were asked, which are very relative to one another. You can get it. Only you should know how to get L1, L2, how to get PL. If you know it, you got the solution of this problem. Very simple problem. Okay, let's move to another simple problem. You can just see. This is typical problem. Such one problem has appeared in the old examination. Hence, I picked this problem. Okay. Now see, assume that the fuel input in BTU, British Thermal Unit, per hour for unit 1 and 2 are given by C1 and C2. 8 PG1 plus 0.024 PG1 square plus 80 into 10 to the power 6. The second one is again 6 PG2, 0.024 PG2 square plus 120 10 to the power 6, outside 10 to the power 6. These are the two fuel cost functions in BTU. The maximum and minimum loads on the units are 100 and 10. 10 is the minimum loading, 100 megawatt is the maximum loading, respectively. Determine minimum cost of generation when the following load curve, load pattern is to be supplied by these two machines. Cost of fuel is rupees 2 per million BTU. See, it's very relative. You have been given a load curve. 00 to 6 am, 50 megawatt is the load on the plant. 6 am to 6 pm, it is a 150 megawatt load. Then from 6 pm to maybe next 00, it is 50 megawatt. It is one cycle. It means to say 6 hour, 6 hour this side, 12 hour, it is a flat 150. Then you have to schedule using these two generators. How economically I can share 50 megawatt for 12 hours, 150 megawatt for 12 hours, and over a day, how it is totally cost effective. Then cost of fuel is given and their production values are given. Let's look into this problem. DC1 by DPG1, incremental production cost of machine 1, machine 2 is taken. It is taken by differentiating C1 with PG1. You can see 0.024 into 2, 0.048 PG1 plus 8 equal to DC1 by DPG1. Similarly, second equation, 0.048 PG2 plus 6 equal to dC2 by dPg2. When the load is 50 megawatt as per the curve. Yes. How 50 megawatt be shared by these two generators? We know that when equal incremental cost criteria is to be applied, dC1 by dPg1 should be equal to dC2 by dPg2. This is all we clearly know it. The same thing is done. Equate dC1 by dPg1 with dC2 by dPg2, which is being done here. You can see this equation is equated with this equation, and Pg1 plus Pg2 must be equal to how much? 50 megawatt. That's what is the second equation. Equation 1, by equating these two, I will get rearranged Pg1, Pg2 constant. One algebraic equation. Another is altogether Pg1 plus Pg2 should meet 50 megawatt. Two equations I'll get. One equation by making them equal, rearranging them. Another is while meeting 50 megawatt, how should be the combination? Pg1 plus Pg2 should become 50. So when I solve these two, you will get 15.625 and 34.375 as their megawatt. Then to generate 15.625 megawatt and 34.375 megawatt respectively, cost of production on this plant, I should locate these values in the respect to Pg1 and Pg2, get the BTU and cost of the fuel 2 rupees per million BTU. I should multiply, get the rupees in total per hour. So how to do it? See here, C1 equal to the value after substitution works out 210.868 million BTU per hour, and C2 works out 373.5 million BTU per hour. It means when I multiply, when I take this Pg1, Pg2 over here, it becomes C1 for me. Okay. Then I have C1, C2 respectively BTU per hour values. Similarly, what is the cost of production by these two machines when they are sharing 150 megawatt? Then I will take, this is case number 1 for 50 megawatt. When the case is 150 megawatt, again the similar scenario. These incremental production cost must be equated to each other, and Pg1 plus Pg2 should be equal to 150 this time. On solving these two equations, I'll be getting Pg1 of 78.126 megawatt, Pg2 of 71.874 megawatt. By using these values in the respective equations, how much I'm going to get? C1 as 851.496 million BTU per hour, and second one is 757.87 million BTU per hour. This is with respect to fuel cost. Product means the cost function gave us per BTU per hour. Now what is being given here? The cost of fuel is rupees 2 per million BTU. Now if I multiply this whole equation after summarizing by the fuel cost, I'll be getting total rupees per hour investment that is required. Let's see how it is being done. Total cost of this curve fitting to meet this curve is given as rupees, you can see here, 210.868 plus 373.5 plus 851.496 plus 752.87 into 2. So whole fuel cost BTU per hour into 2. If I multiply, why I multiplied by 2 here? Cost of fuel is 2 rupees per million BTU. So I have units of C1, C2 as million BTU per hour. So million BTU per hour per million BTU is, it costs you 2 rupee. Then if I multiply this totally by value of 2, it will give me rupees per hour. So I have just mapped this and I have taken it is 52,649.61 rupees per hour. That is the production cost of this requirement. So such one example has come in the earlier examinations. Kindly look, it's very simple. We have to match the requirement of segment of curve for a certain length of observation. What is that load value? How that load is addressed. And for the next segment of curve, there is a shift in the height that is called value. And for that revised load, how is that sharing occur? You just compound it, then you have to take out. This is what is the requirement of this problem. Very simple problem. Only by explanation it is very large. By workout it's very simple problem. Okay. Next. The cost curves of two plants are given like this. C1, C2 in the quadratic form. Again you have been given B coefficients. Correct? Then you have been given determine economic scheduling corresponding to 25 rupees per megawatt hour. Lambda must be 25 rupees per megawatt hour and the corresponding system load can be met with if total load connected to the system is 120 megawatt, taking 4% change in value of lambda, what should be the value of lambda in the next iteration? Of course, such problems will not be there for us. Just it is to view. We will not be having any incremental lambda or change in lambda like problem. But I have included this to just to show you whenever you find analytic procedure for lambda is a procedure. When you read, you may come across, is this there for us? No. Just exact lambda method is there for us. This is iterative method of lambda. A lambda of 25 is mentioned. Incremental lambda of 4% is asked. What is that revised lambda? Like an example is quoted. Just you glance it for your sake. Okay. C1, C2, two equation. Take DC1, DC2, P2, P2. Incremental production cost of machine 1, machine 2. In differentiating it by P1 and P2. Then we have to write the loss. B11 Pg1 square, B22 Pg2 square, 2 times B12 Pg1. This equation already we have dealt in the first problem itself. Correct? Then this was already seen, incremental transmission line loss and lambda 1, lambda 2. Okay. Then for economic scheduling, dC1 by dPg1 into lambda 1 must be equal to, L1 must be equal to dC2 by Pg2 into L2 should be equal to common lambda. This was the scenario of economic scheduling when the losses are there. Okay. This was seen. This kind of work in the first problem itself we have seen up to this point. When we equate it to system lambda, I will get the solutions. So what was the system lambda mentioned here? System lambda mentioned 25 here. Okay. So when I equate this equation, get second equation, let me go back. We got two equations. On solving them, we get Pg1, Pg2. Okay. Then PL we get. It's like a first problem we have solved. Clear? Get Pg1, get Pg2, get PL1. From Pg1 plus Pg2 minus PL, you get demand. This is what we have done already. Next work new is, suppose for 4% change in value of lambda, that is delta lambda, infinitesimally small change in lambda, 4% of 30. Let's see how 30 has come here. Was it 30 or 25? Here it is 30 used. Am I right? This dC1 by dP1 into L1 is 30. Means lambda is 30. What is printed here is 25. So please make a note. This is not 25. This is 30. This is striked out. Please note this where I am circling here. Lambda is 30 in the solution. You can see here. dC1 by dP1 into L1 is 30. 30 is mentioned here. Here also mentioned 30. Okay. Printed wrong there. Okay. 30. Then 4% of 30 means 1.2. So therefore, New connected load of the system was given in the problem was 120. Now change in load is 120 megawatt is the load, and 54.11 was the calculated corresponding system load. The differential load is 65.89 megawatt. Hence, change in load is greater than 0. Change in load is greater than 0. Hence, to get an optimum dispatch in decrement lambda, lambda should be decreased so that it will come to a value of 30 minus 1.2 is 28.8 rupees per megawatt hour. So just know this: if the system load is increasing, lambda must decrease. System load is decreasing, lambda must increase. This is the relativeness of the delta lambda. This problem just give an insight. As the load is increasing and lambda is to be decreased. So 4% value from 30 you subtract. 28.8 is the rupees per megawatt. Okay. Next. Now just see another problem over here, which again on a penalty factor concept, because such one problem you are sure to face in the examination. The system consists of two power plants connected by a transmission line. The total load located at plant 2 is shown in the figure. Correct? Then, data of evaluating loss coefficient consists of information that a power transfer of 100 megawatt from station 1 to station 2 results in a loss of 8 megawatt. See, it's very simple. Two generating stations are connected by a tie line. Load is at station 2. While delivering the load, generating plant 1 incur a loss of 8 megawatt on the transmission line. That's what is the meaning. So, transfer of 100 megawatt from station 1 to 2 in a total loss of 8 megawatt. Find the required generation at each station and power received by the load when lambda of the system is 100 rupees per megawatt hour. The incremental fuel costs of two plants are given by dC1 by dPG1 by an equation. Similarly, second equation. Here, what exactly you are supposed to calculate? This is a different scenario. Load is marked on station 2. Station 1, station 2 together meet this load. That is another scenario. While meeting the load, generating plant 1 experiences a loss. Another observation. System lambda should not be other than 100. That's another criteria. On these parameter, you have to work out what is PG1, what is PG2 for this relevant problem. For this, just see loss equation you have to write first. Whenever you find such a problem, whether the load is on plant 1 or plant 2, PL equation you need to write. What is PL? When two generators are connected to deliver certain load, PL equal to B11 PG1 square plus B22 PG2 square plus 2 times B12 PG1 into PG2. This equation you must remember. The same thing is written here. You can see expanded form. Correct? Now, where is that load? You must see. At load is at plant 2, there is no loss coefficient associated with the plant 2. It means to say this equation will get resolved, simplified. When the load is on plant 2, subscript considering 2, 2, 2, 2, they go 0. Or there is no loss associated with the plant 2. Suppose load is said to be on plant number 1. Yes, plant number 1. In this equation, subscript here in this equation, B coefficients, 1, wherever 1, 1, 1, 1 is there, that equivalent value goes 0. This is what you need to remember. Loss will occur from a plant far away from the load while meeting it. Loss on the station where it is connected won't be there. Now it is in plant 2, B22, B21 are null here. Null here. That's the indication directly. You can see here. Since the power transfer of 100 megawatt from plant 1 to plant 2, that is PG1 is 100, PG2, P21, B22 are 0. Can you see that? B12 go 0. B2. I'm telling you very simple. Where is the load? Observe. Plant 2. Subscript of B coefficient. B11, B12, B21, B22. Wherever there is a 2 in the subscript of B values, they go 0. That's all. All these three terms go 0. What is the meaning is this one only. B11, PG1. That you can see here. PL equal to B11, PG1 square. Suppose you may ask me, suppose load was on plant number 1. Scenario was exactly reversed. Plant 2 was delivering the load. How would be the PL? PL is, can somebody? P22 PG2 square. That's all. Hope you are getting my context here. So this you need to remember. Okay. Then loss of 8 megawatt is incurred. Therefore, PL is 8. 8 equal to B11 PG1 square. So with this, I'll be getting B11 equal to 8 into 10 to the power minus 4 per megawatt. B11 I can get from this. Then I can write what is PL from equation? PL is 8 into 10 to the power minus 4 PG1 square. That's what I can write. Now I know dou PL by dou PG1 if I take dou PL by dou PG1. So the PL equation if I differentiate, I'll be getting 2 times 2 into 8 into 10 to the power minus 4 PG1. Then if I will get 16 into 10 to the power minus 4 PG1, one equation. When I take dou PL by dou PG2, definitely there is no PG2 term, that will be 0. Because load is on the plant 2 itself, there is no loss incurred. Therefore, L1, plant penalty factor for a plant 1 is 1 divided by 1 minus dou PL by dou PG1. If I substitute the above dou PL by dou PG1 in the place, I'll be getting simplified term. As well, I have a constraint. System lambda should not be other than 100. That I will equate it to 100. You can see there. 0.12 PG1 plus 65. What is this? DC1 dPG1 into L1. 1 divided by 1 minus 16 into 10 to the power minus 4 PG1 should be equal to what? 100. That give me simplified algebraic equation. So that algebraic equation contains PG1, PG2. Then together it should meet me the value of 100 megawatt. 100 megawatt is to be supplied by load. Then we know PG1 is supplying 100 megawatt. Then I know that 0.25 PG1 equal to 35 and PG1 I can get. From this, if I simplify, I'll be getting PG1 because in this PG2 equation, PG2 is not at all there here. Correct? Then I'll be getting PG1 itself. So PG1 stand as 125 megawatt. See, it was delivering 100 megawatt, but how could I get 125 here, 125 megawatt here? This should take care of loss itself. Therefore, 100 megawatt was delivered on a line, incurred 8 megawatt loss. Then what was the set point on generator? It is more than 100 at that time. It is 125 megawatt. So therefore, 0.25 PG2 plus 75 equal to 100. When I solve this equation, PG2 I am going to get 100. Then total power received by the load is what is delivered by the first plant, what is generated on the plant minus the loss. That is the actual load consumed on the bus 2, which is 125 megawatt delivered by the plant 1 and 100 megawatt when I have DC2 by dPG2. It is 0.25 PG2 plus 75 equal to 100. Lambda must be common. Then when I solve this, definitely I will be getting PG 2 as 100 megawatt. 125 plus 100 minus the losses, that would result me a value of 212.5 megawatt. This is little relative problem. I'm quite sure it is a relative problem. Such problems are sure to come. So you should be very careful in understanding the requirement of a problem. So where is the load? Those subscript will go 0 in the PL. Identify B11 or B22 respectively. Then using that, get the PL equation. Get the penalty factor of plant 1, plant 2 respectively. Then use that penalty factor and incremental production cost with the lambda given in the system. Get the P1, P2 respectively. Then after P1, P2, get the P1, get the P2, or P2, get the P1. P1, P2 you obtain. Later, subtract the losses, you will get the load. This is how you have to work. So it's very simple problem, but relativeness is there. So you have to have little relative. Such one problem you will find in the Nagarath Kothari also. Okay. Anyhow, I'm sharing this material, you can get into this content. Okay. Now you have another problem which is similarly moving with this. On a system consisting of two generating plants, the incremental costs of production in rupees per megawatt hour with Pg1 and Pg2 in megawatt are given by this. dC1 by dPg1, dC2 by dPg2. Clear? The system is operating on economic dispatch with Pg1 equal to Pg2 equal to 500. So both are equally loaded, 500 megawatt, and dou PL by dou Pg2, dou PL by dou Pg1 equal to 0.2. Find the penalty factor of plant 1. Given that system operates on economic dispatch, yes, it is repeat, Pg1 equal to Pg2. Yeah, I'm solving it exactly. Given the system operates at economic dispatch with Pg1 equal to Pg2 500, economic condition for that optimal operation is dC1 by dPg1 into L1 should be equal to dC2 by dPg2 into L2 equal to lambda. This is the condition. Then I should get dou PL by dou Pg1, Pg2 respectively. It is given. Dou PL by dou Pg2, second machine's penalty factor equivalent calculation loss is given. Dou PL by Pg2 is 0.2. Then using this dou PL by dou Pg2 as a 0.2, I can get L2. How is that? 1 by 1 minus dou PL by dou Pg2. Okay. Let's move to the next heading. You can see L2 is 1 by 1 minus what is given 0.2 here. In this position 0.2 appear. Okay. Incremental transmission line loss of 0.2 is given. I will get 1.25. For optimal operation, we know this condition. I will just use it. Correct? Correct? I transfer, I get L1 into sort out. So therefore, this is how we should be working out. So L1 is missing. Then, similarly, I have determined the incremental cost of received power and penalty factor of the plant shown in the figure. So load is at far away from the generator. PL loss of 2 megawatt, set generation of 10 megawatt, demand of 8 megawatt. To develop load of 8 megawatt, it is scheduled at 10. It means 8 plus 2 is meeting your requirement considering ideal scenario. So determine the incremental cost of received power here and the penalty factor of the plant and the penalty factor of the plant for the shown system, which is here. It's given as dC1 by dPg1. No doubt, when you have been given dC1 by dPg1, L1 can be obtained very easily, 1 by 1 minus dou PL by dou Pg1, which is equal to 1 divided by 1 minus, what is the loss here? 2 divided by, what is the Pg? 10. See here how dou PL by dou Pg is done directly numerically. Loss is 2 megawatt. Generation is 10 megawatt. 2 divided by 10 is the dou PL by dou Pg ratio. Can you see here? 1 by 1 minus loss by generation. This ratio is incremental transmission line loss. This will result you 10 by 8, a value of L1. Then cost of received power is lambda. That is a lambda. What is lambda for this lossy system? dC1 by L, dPg1 into L1 must be equal to lambda. So just mention this value 0.1 Pg1 plus 3 multiplied by lambda 1 should be equal to multiplied by L1 should be equal to lambda. You can just see 0.1 Pg1 plus 30 into whole bracket 8 10 by 8. Okay. Then Pg1 of 10. Pg1 is scheduled at 10 megawatt. So 0.1 into 10 plus 30 outside the bracket 10 by 8. So it is 5 rupees per megawatt hour. So while dealing this interaction of 8 megawatt, power received at this bus is rupees 5 per megawatt hour. So you are selling it at less than this, you are at bankrupt. You must see to that. What is that delivery you are doing here? What is the cost of power received? Your transmission line losses, your incurred expenses must be taken out of this, then your corporation will be under the profit. In that way, buying and selling of power, trading occurs, there this kind of economics is taught there. Okay, it's called as cost of received power. Where do this comes? Interpretation of penalty factor. Penalty factor is indicator of how costly it is incrementally produced megawatt. That's the indication. Then how costly is that obtained by penalty factor of L1, L2, L3 like that. For economic loading, incremental fuel cost into penalty factor should be same. On that context, approximate penalty factor issue has come. That has led to an analysis of how costly is that, what is that cost of power received at the load side evolved. So this problem come to penalty factor and approximate penalty factor concept of representation. Problem is very simple. Just in 2 lines you end up with a problem. But dictation is very large. With the diagram, it makes us very large problem, we cannot touch it. No, it's a very simple problem. You need to touch it very intelligently by looking to the requirement. Okay. Here also similar thing. A 2-bus system was given to you, cost functions, and you have been given lambda 26 rupees per megawatt hour. Then coordination equation, one of the derivation we come across, incremental fuel cost plus lambda into dou PL by dou Pg1 equal to lambda. This kind of equation. This is not there for us, but you can just go through this problem, which I am just sharing to you here itself. Whatever the penalty factor method I work, by coordination method also you can. This is solved side by side. I feel so. I'll just move out. You can see here. This is being solved. This problem is being solved by coordination equation method. dC1 by dPg1 plus lambda into dou PL by dou Pg1 equal to lambda, where PL is given. PL is given, loss is given, then B11 is given, then definitely load is at plant 2, only B11 is the effective here because load is on plant 2, subscript of 2 dissolves, 21, 22 goes off, 11 only remain here. Okay. Then using this equation, when you solve, you get Pg1. So then you substitute coordination equation plant 2, dC2 by dPg2 lambda into this thing. Okay. Then I will be getting second plant, dou PL by dou Pgi. Can you see this? It goes 0 because there is no loss incurred at plant 2. Why? Load is on plant 2, there is no loss in the plant 2 itself. That's the indicator. 0 over here. Hence it is 0. Then you will get equation. When I solve it, I will be getting Pg values and loss values. Then load is Pg1 plus Pg2 minus loss. This is by coordinates equation. The same thing if I solve a penalty factor method. Penalty factor of plant 2, plant 1, I can solve this way. 1 by 1 minus dou PL by dou Pg1 and For economic scheduling, it should be equal to lambda, which is 26 rupees. I get PG1. Plan 2, lambda 2 must be, L2 must be 1, because 1 by 1 minus 0, it is 1. So it is 1 into DC2 by DPG2. It is lambda. It is 26. It stands as 66.6. This is quite easy. Penalty factor method is easy. Coordination method is using this equation. DC1 by DPG1 plus lambda into dou PL by dou PGI equal to lambda. With this equation, we can solve as a coordination equation method of solution. Penalty factor method of solution is replicating L1 L2 and making DC1 by DPG1 into L1 equal to DC2 by DPG2 into L2 equal to lambda. I get the value of P1, P2. Once I get P1, P2, next is to get load and loss. And just see PL equal to B11, PG1, because load is on plant 2. There is nothing as a, such a load from machine 2. Machine 1 only suffer load loss. It is B11, PG1 square. Write it. 9.15. Absolute the same value will get 9.15. Right? Then take sum of PG1, PG2, subtract this. You will get 147.12. The same thing you got. Clear? Similarly, I have some more examples which outline similar concepts. Clear? Yes, we can go through. Now, this is interesting problem which we need to discuss. This is on B coefficient method. You have learned what are B coefficients? Transmission line loss coefficients. So, B11, B22, B12, B21 concerned to two machine system. How those losses are calculated? You remember the derivation. And what is that value of B11? What is B22, B12 in terms of bus power V1, bus voltage V1, bus line connected transmission line resistance section RA, section RB, section RC, like that. For this problem, we need to understand very carefully how current distribution occur, how resistance of each section is important, like that. Let us concentrate on this problem. Such one problem you may encounter in the examination. For a system shown below with the bus 1 as a reference, bus 1 is reference with a voltage of 1 angle 0. When it is a reference, normally 1 angle 0 pu is the reference. Find the loss formula BPQ. It means B11, B12, B22 you have to identify. If the branch current and impedances are like this, IA current flowing in section A. Now B current flowing in section B. C current flowing in section C. ZA impedance of section A. ZB impedance of section B. ZC impedance of section C. What do you mean by this? Just a moment. I'm sorry for the interrupt. Am I audible to you all, please? Am I audible? Hello? Hello? Am I audible?
Yes, sir.
Okay. All of you are there or not? 36 count is there with me.
Yes, sir. You are
Are you
audible.
there? Yeah, thank you, thank you. Because no one is replying in a hurry, that's why I wanted to, because I just got interrupt in between. I just close that interrupt. Okay, this is a new problem. I need to discuss carefully because this type of problem you are sure to get in the exams. Okay, so here we have two loads. One is, and on the bus one there is a transmission line ZA impedance. A is marked here. This is called section A. You can see my pointer. A is impedance of the line, then there is a load. Here B, from the bus 2, there is an impedance of a transmission line ZB and a load. Between 1 and 2, transmission line is there, whose impedance is section C, ZC. This you have to understand first. ZA is impedance of the line delivering load part 1. Impedance of the line ZB is delivering load part 2. There are two loads. Total load is load 1 plus load 2. Part of the load is dealt via the path ZA. Second part of the load is dealt with the path ZB. Now path ZC, impedance of ZC is common to this. There could be a flow of power from 1 to load 2 via C, or there could be a flow of power from plant 2 towards load 1 via ZC. That's called ZC impedance. ZA is on the plant 1, bus 1 to the load 1. ZB is from the plant to the load 2. ZC is common between plant 1 and plant 2. That's the arrangement of the mechanism. So you have been given currents in each section, impedance of each section is given, and base of 100 is considered. Okay, then you just see this sum ratio, current division ratio. IA, the load current flowing through this branch is IA. Whatever the current flowing here is the current flowing out of the load. Here IB, whatever is the current flowing here is the load 2. I mean to say total current from the system is IA plus IB. That is the load total. Then from the first bus perspective, IA divided by IA plus IB, I take a ratio. That ratio stand as current IA, whatever I have here, 1 minus J.15 divided by sum of IA plus IB. If I add them, 1.5 minus 0.2025, 0.25, is it right? 25 or 20? 1.5, 0.2, should be 2i. This 1 plus 0.5, 1.5. Correct? The second is 0.15 plus 0.05. It should be 0.20. So it is changing 0.25. Denominator printing mistake is here. Okay. If 0.25 is the answer, we should change here this to other number. Okay. This is ratio IA divided by total loads. This is called fraction. Fraction of load coming via A. That's what I calculated. Fraction of load coming from B, I will calculate similarly. That's called IB divided by IA plus IB. IB current divided by IA plus IB current. If I do IA plus IB means what? Load 1 plus load 2 together. If I arrange them, that become current flowing out of bus 2 via ZB impedance, that is 0.335. If I add these two, that will become 100%. It means 66.5% load is delivered via this, remaining 33.5% load is delivered in this way. That's the meaning of this ratio. What I am doing? Load flowing from ZA section to the total I calculated here. Load flowing out of ZB section to the total I calculated here. That stand as IB by IB by IA plus IB, and another one was IA divided by IA plus IB. So now current distribution factor were like NK. I calculate. Now we can see NA1. Current distribution factor of section A when generator 1 alone is dealing the load. Alone dealing the load. That is IA plus IB. If I take that itself is 0.6649. Then NA2, the current distribution factor of this plant or this section when generator 2 alone is dealing. Before that, let us do it. Let us, like NA1, let me do NB1 also. What is NB1? Current distribution factor when plant 2 alone is dealing. You can just say NB1. This way. How it's going? Yes. Similarly, current distribution factor from plant 2 perspective. So here NB2, NA2, NC2 I should calculate. It means here I have current distribution factor calculation. IA divided by IA plus IB. When I take numerator IA to the ratio, that become NA. If I take IB, it become IB. If I take IC, it become IC factor. Same thing is B. NA1, NB1, NC1. In the numerator, I will change IA1, IA, IB, IC respectively. I operate it. When delivered by plant 2, it is there, this current. IB, I'll take here. 0.66, 0.359, 0.649. Now, bus 1 is said to be a reference bus in the system. Then, voltage of that bus is 1 angle 0, 1 angle 0 pu. What is the voltage of this bus at that time? Voltage from this bus to this bus is computed as reference voltage, current flowing through this, impedance of this. You can see here. V1 plus IC into ZC is nothing but V2. You may ask me why it is required. When I want to calculate V11, V12, V22, I am certainly requiring V1, V2, cos phi 1, cos phi 2, sigma 1, sigma 2, P1, P2, like that values. To get into those values, I have to start from given one bus reference. What is the value of second voltage? I have to calculate by theory. So therefore, V1 is said as a reference, 1 angle 0. V2 is not mentioned. V2 is by just a drop. V1 plus this drop, if I add, that becomes V2. I have to keep it ready. This becomes V2. Then the total injection from Gen 1 side. Gen 1 side, you can just see, which is IA minus IC. IA minus IC. Correct? IA minus IC. Then IG2 side, it is IB plus IC. You have to watch the arrows here. Why it is minus here, why it is plus here. These arrows were predefined by the problem. It means I had to apply KCL at this bus. KCL, that's a simple logic. What I1 or IG1 generator injected current is equal to IG1 equal to IA minus IC. What is coming here? You can see IA minus IC. From this bus perspective, IG2 equal to how much? IG2 is IB plus IC, because these were already marked. We are not going to change them. What is marked on that reference only calculation runs. Therefore, from the generator injected current perspective, IG1 or I1 is equal to IA minus IC, and from IG2 perspective, IB plus IC. You can see. So why I am getting these things? Why I am doing this? I require sigma 1 here, sigma 2 here. the angles associated with the currents of each bus is required to me. I require power factor angle. I require current vectors angle. Hence, I have to calculate injected current at Gen 1 or bus 1, bus 2 from the relative values. Then we know this I1, I1, I2 are nothing but Ig1, Ig2, like I1 sigma 1, I2 sigma 2. So I'll get this is sigma 1, this is sigma 2. I got it. Then cos of sigma 1 minus sigma 2. Difference I want. Difference is what I want. Then cos phi 1 angle of this particular, where is this? Cos 7.1. This I have to calculate. Then cos phi 2 angle between V2, Ig2. What is the power factor? Power factor is the angle between plant voltage and plant current. V2 and delta V2 I2's angle is cos phi 2 and I take become power factor. Like that, the angle of V1 I1. V1 I1 is 7 point because it's very clear. Ig1 is 7.11. V1 is your reference. Reference means angle 0. 0 and this difference, that is 7.11. Hence, cos phi 1 is cos of 7.11. Then cos phi 2 is cos of angle between V2 and Ig2. V2 is no more 0, it is 2.76. And delta sigma 2 is minus 12.09. Between these two, a difference, cos of that. Are you clear? That stands as 0.9666 like this. Okay. So I'll be getting now what is B11? V11 is 1 divided by V1 square cos phi 1 square here. NA1 square R1 or RA plus NB1 square RB plus NC1 square RC. This was a summation. You recall back the derivation. There was a summation block, summation of NAK RK or NK RK was a summation. So that K, when we expand, how many interconnections exist as a K number of branches, that many products of term N into R results. Here I have three sections. A section ZA is given, in which RA is there. RA, XL is there. ZB, there is ZB, RB and XLB is there. ZC, there RC and XL is there. For that only RA, RB, ZC, I mean RA, RB and RC only I take out from that impedance. You can just see here 1 divided by 1 square cos phi square NA1 0.6649. This is what we have. 6649 square plus RA 0.02. How I got this RA? This RA is available in the ZA here. RA only this term. This is not used. X is not used. RA, RB, RC. These are used to calculate the loss. Can you see? RB. Can you see? Sure? Sure? RC. This calculation results you B11. Divided by 100 makes you per megawatt. Similarly, B22, same equation, V2 square, cos phi 2 square, wherever you had 2, it become 1, it become 2. This means this set of equation, these you will be using. These you will be using in the second scenario. You can see. Into RA, into RB, into RC. Then calculation of that will do B22. Divided by 100 you do, it become per megawatt. B12 requires some different What is that? Cos of sigma's difference. V1, V2, cos phi 1, cos phi 2. All these we have calculated already. Here, wherever you had square RA, square RB, square RC, both a term RA, both a term RB. We will see here. 1, 1 RA, 1, 2 RA, 1, 2 RC. So 1, 2 RA, 1, 2 RB, 1, 2 RC. You take a product of this, that become what? This is new problem to you, very much new problem. You have to understand carefully. How is that load division takes place? Total load you have to identify. Total load you have to identify. How current flowing through one section is of what percent of the total load? What is the current division factor of that section A, section B, section C? You have to calculate this way. So like NA1, NB1, NC1. When Gen 1 is dealing this kind of calculation. When Gen 2 is dealing this kind of calculation. These were used in the calculation of B coefficient. Maybe in the next problem you are able to get more insight. Now you just see this another sequence here. This is another problem, two plants, plant 1, plant 2. Some interconnection is there. There is a load 1, load 2. Now identify how many sections are there. A, B, C, D. These many sections are there. 4 sections are there. So Gen 1 is injecting to bus 1, Gen 2 is injecting to bus 2, I1, I2 or Ig1, Ig2 from the Gen 1 section A. From the bus 3, you can see bus 2 is here, bus 1 is there, bus 3. There is a flow of power to bus 4 via impedance ZB. Then from the 4th bus, there is a load flowing out. And here from the bus number 2, directly it goes to bus number 5 via Z, impedance ZD. Then there is a load 2. Now no matter, total load is load 1 plus load 2. How it is flowing? Which are all the elements responsible for the loss calculation? We have to correlate. For that, just see the problem. For the system shown below, bus 3 as a reference here. This bus 3 is the reference. How much is the voltage? 1.2 angle 0 is the reference voltage. Find the loss formula coefficients in PU, and all are mentioned here. Okay. Now you know that all are pre-marked. I have not marked them. Pre-markings are given. You know I1 is marked, I2 is marked, IA is marked, IC is marked, IB is marked, ID is marked, load 1, load 2 is marked, and voltage also marked. Now IA is given, ZA is given, ZB, ZC, ZD, like this, base of 100 for the calculation. Now, what is the total load flowing here? It is the IB. What is the load flowing out here? ID. IB plus ID. If I count, that is the load 1, load 2 total. You can see how it is being done. IB plus ID in the denominator. To that IB plus ID, what percentage of the total load is coming from this branch? Bus 4. What is the dispense of power from bus 4? If I want to know, IB divided by IB plus ID, if I take, I'll get percentage of the load through this 4th bus. To know the percentage of this, what I will do? ID divided by IB plus ID. If I do, I will be knowing percentage of the load dealt over here. Together it's become 100%. You can see the same thing here. IB divided by IB plus ID. ID divided by IB plus ID. It's very clearly mentioned. Very clearly mentioned. So it is IB 4 minus J 1.5. IB plus ID. This is the fraction. It's called ratio. Second one also ratio. Okay. Now NA1, NB1, NC1, ND1 are the respective current distribution factor when load is dealt through generator 1 alone. You just see here. You just see this one. I'll just go back. When load is dealt by this only, this line is important for me. Yes. This line is important for me. Yes. This line is also important for me because load is dealt via this way. This is also important. This is also important. But this is not going to deal at that time. Correct? Look at very carefully. I repeat. When plant 1 alone deliver the load, entire load, how the current flow? I1 through ZA, ZB to the load. And from this bus, it will go opposite to this mark. No matter. It will go, it will reach second load. So this has fulfilled by plant 1. Then I am able to calculate of the total load, how much is the current division takes place in this branch, in this branch, in this branch, in this branch. I have to calculate. Then when generator 2 alone delivers, 2 alone delivers. Now see how current can flow this way, down to load. One path, some percentage of the load. Then remaining load will go this way and this way and load. Now what about the ZA here? This section is not in the picture at all because load is flowing via C to the B to the load. Then this is not at all responsible. That's the reason you can see here. When generator 2 is delivering, section A is not contributing. Ratio of current is 0 there. No current is flowing on that section. Because this is very clear. Current will flow through this way and to the load. B and C section. A is not there. When it was delivered by plant 1, absolutely all are involved. You can see all are involved here. A, B, C, D. Yes or no? Involved. Now, how is that A1? Whatever is the current coming out here is the 100% of the load current. I1 is nothing but load 1 plus load 2. When plant 1 alone deals the load, I1 must be equal to load plus load 1 plus load 2. Then ratio of current I1 divided by load 1 plus load 2 should be equal to 100%. Suppose 100 ampere flows here, all 100 ampere has to come out here. Then current distribution factor for section A stand as 100%, nothing but 1 for that. That's what is written here, 1. Then B section. What is B? B is here. You can see here. B is here. Now what is B? B itself is the load delivered in the part 1. Then what is this B? B is known to me here. What is B? That is 0.575, 57.5. Ratio of IB to the load current is 0.575. Same appears here. Correct? Same appears here. B. Now, B is obtained, A is obtained. What about C and D I should do? What is D now? D is nothing but load 2's contribution and load C. I will see here. What is C contribution? C contribution is, just see here, 0.425 minus. What is this 0.245? Look at this. What was the total load? Load 1 plus load 2. How much has been dealt here? IB portion dealt here. What is left here? ID portion. What was the contribution? Here. Contribution was 0.425. ID through contribution was 0.245. Now, direction of current is, it is trying to push the current in this way, but originally marked in this way. Therefore, it is minus 0.425. Minus 0.245. When it comes to D, straight 0.425 and to the load. So, minus 0.2425 minus 0.425 is the current distribution factor of C section. Plus 0.425 is the current distribution factor of means section D. That means exactly opposite work. If I speak now only, when plant 2 alone deal the entire load, let's imagine this is dealing. What is the contribution over here? 0.425. Then distribution factor for D must be 0.425. Am I right or not? You can see here. Distribution factor for D is, where is that D? Point, where is that D? This one. When D is dealing, where is that D? Here. And what is this C? These two together, when it pumps, IC plus ID, together deliver 100% of the power pumped by this. And it flow through C, P and to the load. It flow through D and to the load. Then see how that division takes place at C, D and at B. B and C must be similar. Let's go back and see how much is at B. So at B it works 0.425. 0.425. So it is 0.425. Is this correct? 0.425? Yes. Then if 0.425% goes to here, what is remaining here? 0.575% go through D, and these two together remain 100%. Whatever is flowing through B, where is that B? Must be the percentage C. There is a print mistake here. Kindly note here. This is a mistake here, print mistake. 0.425 and 0.575. These two are wrongly printed. This is wrong print. Just check this. 0.575 is not D. What is D here? D is 0.425. So B should be printed here. D should be printed here. So there is a wrong print in the computation. So 0.575% of the 100% will flow here and here. Then 0.425 will flow here, because we know what is ID ratio, what is IB ratio, whether it's delivered via plant 1 or plant 2, no matter. Finally, it goes to load here. This is going to load at 0.575% of 0.57 of a total, and this is 0.425 of the total load. Therefore, this is now dealt from plant 2. Then this is dealt from point 2 means 0.75 should be equal to 0.75 here. This is ideally thinking. 0.575 is here. This must be 0.575 only. You can see here. That's what I'm speaking. 0.575 is NC. What about NB then? NB must be 0.575. Then definitely A is not involved. A is not involved because A section is behind this. This is not involved. And D is the load. D is already written as 0.425. So please revise these things in your notes. This value must be written here. This value must be written here. Accordingly, you got the NA1, NB1, NC1, ND1, NA2, NB2, NC2, ND2. Using these values, I can compute the B coefficients. That's again, I don't know the values of voltage here. V1, V2 is not given. V3 is given. V3 is 1.2 angle 0. Then 1.2 angle 0, IA into ZA. If I add up, it becomes V1. V3 plus IA ZA is V1. V3 ZC IC is I2, mean V2. I have to calculate voltage here, I have to calculate voltage here, reverse. V2 mean V3 plus IA ZA is V1. V3 plus IC ZC is V2. You can see the same thing is being done here. Where it is being done? V reference plus IA ZA. Am I right? Then V reference plus IC ZC. I have to do it. So from this, I'll get values of sigma 1, sigma 2. Then cos phi 1, cos phi 2. Rest of the work is same. Then the ratio B11 is 1 by V1 square cos phi 1 square, summation of this. Three terms. 1, 2, 3, 4 here, because we have 4 sections and work. 1, 2, 3, 4, D up to D. Which are responsible have a meaning here. Which are not responsible don't have meaning here. You can just see. Clear? Because B2 to B1 to all these divided by 100 become permanent values. So this way, this subject has come to a conclusion. So this